Okay, so Pradyut, what have you learned about the Dyson series?
Um, oh wait, so yeah, so essentially, I got the idea that it's the propagator, some sort of a propagator, in terms of time, and then you have like sequence, like you just break down T naught to T, and then you just break it down into T1, T2, and so many parts. But then the question is, why does the potential crop up when you try to work on the Dyson series in the
Hmm.
expansion? So yeah, that was one question I had.
Yeah, okay, we could try to understand that. So, the starting point of the story is something called the interaction picture. So, the idea of scattering theory is that you want to try to answer the question of how do some initially free states, right? So just initially free particles,
Mhm.
undergo some mysterious process of scattering and come out again as free states, right? So
Uh-huh.
you want to try to contain the story of interaction within the Hilbert space of the free theory,
Uh-huh.
right? So what you do there is leverage the fact that I know what the free theory's Hilbert space means pretty clearly. So in quantum mechanics, it's not hard to access the interacting theories Hilbert space too. It's fine. Right? You just solve the Schrodinger equation.
Mhm.
But in context like quantum field theory, it could get pretty difficult. It could get pretty complicated. So okay, you have some intuition for what a free vacuum looks like, and what excited states in a free theory look like. Essentially, it's either, I mean, it's kind of like a Bose or Fermi gas. That's really all it is. Some relativistic Bose or Fermi gas. You have a
Mhm.
state with one free fermion, two, and then you could
Yeah.
compute the thermodynamic quantities, and they're essentially like a gas, and that uh, their interaction is just flyby. They just don't interact. So
Mhm.
this is like this is kind of very ideal version of a gas too, but that's that's your zeroth level intuition. The point of scattering is to say that within this Hilbert space, right, what interaction does is lead to some kind of mixing between these states somehow,
Mhm.
which means that if I
Yeah.
started with let's take some reasonable number of four particles, each with
Mhm.
some momentum, p1 to
Mhm.
p4, then I let the scattering process occur, and then I look at very late times at what happens, and I now have four particles or more, depending on what the interaction is doing, right? Because you could have particle production processes, but still, you have some set of momenta, right? And these are all sort of definite eigenstates of the free Hamiltonian, free moment, like the momentum operator, and you could actually just compute their energies too, as p squared
Yeah. Yeah.
plus m squared, right? This is like this is just the free Hamiltonian. So the interaction picture wants to compute the this mixing, let's say. Right? The aim is to ultimately compute this mixing, and so you need to sort of separate out the how should I say? You want to separate out the potential from the kinetic part, because the kinetic term is the free Hamiltonian.
Oh, okay.
That's really all it
Okay.
is. And the interaction is going to be dictated by the potential,
Oh,
right? So
okay.
this is the same whether you're doing quantum mechanics or whether you're doing field theory.
Mhm.
It's all identical. So there is a slide in this talk which deals with that. I'll try to pull it up in a second. So let's see. Oh, we could try to first build our intuition for it, and then we could try to understand how the series comes about. Uh, I'll just share screen. Okay, desktop, keynote. Okay. Right. So this was our expression, right? So you're looking at, in some sense, the evolution brought on by the interacting part of the Hamiltonian, or like by the potential, right? So the easiest way of separating out the kinetic and potential terms is this thing here, right? So the reason why you're adding this conjugation by the free Hamiltonian is something that we should probably figure out, right, before we proceed any further.
Yes,
So
so probably like you're just doing the you're just kind of imposing like you're kind of extracting v out of the like if you take
okay,
the exponential, it's a unitary operator,
yeah,
so you're just sandwiching the v between the unitary operators that is trying to extract the potential out of it and
right.
separate out the h naught from the potential, right?
So how would we see this? Um, so if I have like, okay,
um,
s-
so using the
wait, why am I
bracket
compelled to do
formalism.
this?
Hmm?
Why am I compelled to do this? This hi like this?
So the bracket formalism, go from okay, not
Okay, let's
fair.
open up another window where we
Okay.
can start to write things. Okay,
I'm not.
so let's share a different screen, which is this Untitled 2. Yeah. So we had an expression that looked like this.
Is it para minus I h d?
0.
It's not d.
So T, you're correct.
I h not d.
Let's see if I got the minuses in the right order. Yeah, there's a plus and then there's a minus. And here, kinetic term is just p squared. So h naught.
Okay.
Oh, sorry.
Yeah.
Hmm.
The minuses are like interchanged, I think.
No,
It
no, I
is
think. No, I think
it is interchanged. Yeah, I
it
just
is
cross
okay.
checked. Yeah.
Cool.
It's minus and
Then I
then
could
plus.
change that.
Wait, is it? I thought it was right. Never mind.
I have written it down, so I just cross checked. Yeah.
Oh, that's right. Yeah, this is the forward evolution. Yeah, that's true. And that's
Right.
conjugation.
Okay,
Yeah.
that's a good thing you said right there. You said forward evolution and back. So this would evolve forward. This would evolve back.
Yeah.
So the intuition is that when I apply this on a state, right, what happens? It evolves it forward by the free Hamiltonian
Right.
by some time t.
Right.
And then I apply v, right? Or so let's say v happens.
Mm-hmm.
And then I evolve back. I evolve
Oh,
back.
So you're just doing the bracket
So
thing, right? Like, it's like writing out the H naught, sandwiching V between H naught and H, like H naught. And so whenever you want to compute the final state, you just move V, multiply V with whatever the right side bracket, and then whenever you want the initial state, you just do the conjugate of that.
yeah, exactly. So the
Yeah.
point is that I'm trying to. Okay, so it's a question of how we think about. Let's say where we're putting our states, right? So are we putting our states all at some time, some initial time, or are we trying to think of them? Um, I mean, you don't really want to disperse them in time per se, right? So you have some initial Hilbert space where you're convinced everything is free. And then you have some
Mm-hmm.
final Hilbert space where again you're kind of convinced that everything is free.
Okay.
In between is where you don't really know what's happening. Right?
Mm-hmm.
So, like if I take this state, which for lack of, yeah, I don't know, it's some momentum, right? So this is some, could be, let's see if I can get the notation to come out. There's some set of momenta, right? Some number of particles, and it's at time time 0. Now, what will happen is that under the action of the free Hamiltonian, so this is in the free Hilbert space, right? So this state satisfies sorry, I used the wrong notation here. I partial t initial
right. Yeah.
And so what I want to do in thinking about scattering is evolve this initial state using this Hamiltonian. I think it's a minus, I don't know. Somebody help me with this, but fine. I evolve it with this Hamiltonian, and then I apply V, right? That's my interaction, and then I evolve back.
Right. And then you pick up some terms.
Yeah,
Essentially.
exactly. So that basically means that we can, I mean, if we want, we could try to work out what, oh yeah, we could try to do this. Like, who is H sub I of t, the Hamiltonian on the right-hand side of the Schrodinger equation for?
It would be some kind of.
I mean, it could very well be that it's not for anybody, but presumably we can find ourselves states
Right.
for which
Yeah.
this is the right thing to be thinking about.
During the interaction, or wave
Yeah,
functions
exactly.
during the
Something like
interaction.
that.
Yeah.
If we had state at some intermediary time, then we could probably say that this guy's like our interaction Hamiltonian.
Right. Right.
So, well, okay. Another thing that we know is that you can write down the evolution equation in such a way that the easy part, the free part, can be separated. Right? Like let's take the overall evolution operator, not the
Oh
U I
yeah.
write down in my
Um,
mhm.
So yeah, so this is what I remember vaguely from QFT.
Uh-huh.
Going back to the S matrix. Yeah, so this was like kind of astounding for me because like so you have the S matrix and whatever states don't interact, you can clearly separate them out and you show that the V or the S matrix of interaction is zero there. So yeah, so it evolves. The initial if the initial state and the final state are equal, then you don't have intermediary state. So I mean the mathematics of that is that what we are trying to work out right now?
Roughly, if I understand you correctly, then yeah. So you want, okay, so let's see if we can actually get to the bottom of where the interaction picture comes from, right? So what do you want to do to make this the solution of the Schrodinger equation for somebody? Like if you wanted to go after these states, like the structure has kind of been laid out for us, right? Like the fact that there's this e power minus iht encourages me to consider states of this form. So I'll call this, and I'll apply
Local. Yeah.
I'll call this our trial wave function or trial state. Psi trial. Yeah, that didn't come out right.
Yeah.
So what happens now is that if I apply h sub I, then the h naught factors will cancel, and then I just have v acting on psi. But we need to work backwards. So it means we have to work to figure out whether, so we know that this psi satisfies the ordinary Schrodinger equation with the full Hamiltonian, yeah? So let's try to work backwards from that. These are all painfully basic things probably for some people, but when you learn about it first time, this is what you want to make clear, right?
Right.
So what I know, are my conventions minus? Are these the right conventions? I don't know. Let's continue and figure it out. Equals our full h. Yeah.
Yeah. Yeah.
Right. So now when it hits this
I
guy,
think there's no minus sign. I think
there's no
it's
minus.
just,
Okay, I
yeah.
think you're right.
Yeah.
Okay, so now what does this imply? I hat h not t t, right? Equals full Hamiltonian acting on what we got here.
Yeah.
Now let's see what we can buy ourselves. The left-hand side
Oh, okay.
equals, there's no minus, you said, right? So I don't know why
Yeah.
I'm
No
carrying
minus.
but there's an I.
Yeah.
Now there will be a minus. H naught times this whole mess.
That's not, yeah. So that's not. Side
So let's
track.
be careful. So let's see where this goes. If H naught is, yeah, right. This is true. And it doesn't matter because H naught and e power minus I H naught t commute.
Yeah.
Right. Otherwise, I'd have to be a little bit more careful.
Yeah.
And we're gonna have. So you know what? I could just take. Okay. Let's go in steps. Let's go in steps.
Oh, acting on the side track. Yeah, and then you have the separate. Yeah.
Okay, and then I have this e power minus I hat H naught t. Okay, so let's write this as power minus I hat H naught t. Nope. Times H, okay, minus H naught, just an operator, plus I partial sub t acting on side trial.
Oh. Okay.
And the right hand side is just yeah, okay, let's also write the right hand side actually. Actually, how will we write down the right hand side, I wonder? So what do we want to do? Is the RHS just going to be the way it is, or do we want to manipulate it somehow? Okay, equals not Mathematica. Let me add some more space here. Yeah. So I write down the expression that we had up here. Add H. Just to remind ourselves, this is what we had, which is hat H e power minus But now we want to get this e power minus I H naught t to the left hand side.
Yeah.
What are we going to do? We could take an infinite number of commutators in some sense to have to pull this across.
So you just expand the exponential. You just generate a Taylor
Yeah,
series.
sure. I could do that, but is there something clever I could do? What is that infinite commutator? If you want, you could think of it that way.
Infinite commutators. Would it be some sort of a propagator?
I mean, or
object,
alternatively, we could just not do that, move e power minus I H naught t all the way to the right, but we're not going to get anything interesting out of that, right? Like on the left hand side, because we're not comparing the things that we want to compare.
Yeah.
Yeah. Because we want things to be acting on side trial.
Right.
Okay. So
maybe we can cleverly play with inserting one. This is what normally helps. It's not to say that it'll really solve our problem, but it's something we can try. Okay, so how would we insert one? What's the convenient one to insert at this stage? The convenient one to insert would look like e power I hat h t, right? Times e power. It's going to be e power minus hat. Well, no, that's not really going to help us. We're just going to end up back with the same thing. So maybe we do have to deal with this infinite commutator. Clearly, one term just passes straight through, if you think about it. Right, because we know how h is given as a split between h naught plus v.
Yeah.
Oh, okay. Right. Right. Okay.
I hope that you guys are noticing that I don't actually know every step of this procedure right at this very moment.
Yeah.
It's an assumption that you're making. You're just categorizing everything that is not, H naught as V. That adds up.
Yeah. I mean, that is what we mean by V. It's more just a definition.
Yeah.
It, I mean, is it?
Yeah.
I mean, like, is everything that is not the
Kinetic term potential?
kinetic
Yeah.
terms? Yeah.
Yeah.
Okay.
Well, okay, you could have a higher powers of the momenta or something, but that's a bit above our pay grade. Even there, you in principle do think of these other things as interactions, as derivative interactions.
Okay.
Yeah.
So,
Okay. So you're not okay. Yeah. You're not categorizing what type of interaction it is, just calling it some kind of interaction.
exactly. Exactly. So now let's split this up. Yeah, there's gonna be what? So there's one term which we can already
H naught too.
Oh, there's an I. Make sure we get that I. Times acting on maybe I used the wrong symbol. Very possible. And the other term, which is at V E. There's no symbol like that? Okay. Is this clear up to this point? Now, clearly we've gotten some sign wrong. Maybe there really should be a minus. Rahul. Because look at what's about to happen.
Right.
Okay, so major update in our information about the universe. There's a minus here, which means there's going to be a minus here, which consequently means that there's going to be a plus here and a minus here.
Yeah.
Right? Which then implies an overall minus here. Great. So that H naught can cancel with H naught here.
Mm-hmm.
right?
Yeah.
And we have, once again, a consistent Schrodinger equation.
Mm.
Right? Okay, so look, this term. So let me not write the minus outside. That was just me being lazy for, pushing the effort to have to deal with it later.
Right.
Okay, so now the this H naught and this H naught cancel.
Yeah.
Right? And we're left with something we can simplify. Minus I H naught times T times minus I partial T. And so we have our equals V e power minus I hat H naught T yeah. So great. Our trial was the right state. Which implies that this I partial T of, I'll call it interaction now.
This
Equals,
is actually just saying that the operator I minus I dou by dou t is nothing but the potential. So,
well,
instead of
not quite the
exactly
potential,
explaining
right?
okay.
It's the potential with the dressing, where now H sub I equals what? It's our expression.
That's not
Yeah.
T at the,
Minus.
I think that the minus is on the right. Yeah, minus is on the right.
yeah. Oh, okay.
That didn't come out right.
Yeah.
Great.
Right.
So, unsurprisingly, if you evolve, or okay, so if you backwards evolve your wave
Right.
function to some through the free Hamiltonian,
Mm-hmm.
right? This expression here, then you get a state psi sub I who satisfies this Schrodinger equation with the Hamiltonian we were looking at. Now, this really is the multiple commutator between V and H naught, if you really look at it.
Right.
You have to keep taking these nested commutators. If you
Yeah.
expand this, you just want to take it to the right. Because
Yeah.
you could say that if I just pull this all the way to the right, then e power minus I H naught t will cancel against this. But that's going to be a sequence of commutators with H naught and V.
Yeah.
So in some sense, we
Right.
got around having to deal with actually taking the multiple commutator. But let's see how we could have done it here. I mean, maybe we could have just multiplied both sides with e power I H naught t, and then we would have come to the same result, which is what we did at the end. So yeah, great, multiple commutator. Which is this is a compact way of expressing what you get, but there's a lot going on here
Mm-hmm.
because X and P don't commute, and
Yeah.
that's actually a slightly fearsome thing to deal with. Anyway, the Dyson series lets us to work around all these things. So
Mm-hmm.
we could mhm, we
Yeah.
could get back there. Any questions though?
Yeah. Okay. I mean, if we are done with this particular topic, I had one more question. Yeah,
Well, I
which
mean, we
was
haven't quite
We're not.
gotten back to
Yeah.
our the series,
okay.
right? Which
Yeah.
you wanted
Series.
to then expand.
Yeah.
Yeah.
So
Well, I mean, how mysterious is it? Do you feel like it could just be that the rest is kind of obvious, but could also be that you want to understand it better?
mhm.
Because what were these propagators doing there, right? Like, what were all these
Mm-hmm.
I over E minus P squared over 2 plus I epsilon? You had all these things coming in.
Yeah.
Like, what exactly is that? Why is it? What is it doing there?
Mm-hmm. Right.
So we could just try to work back. I mean, we don't have to do the whole thing because that's a slightly laborious exercise. But guys, actually, I have to take a brief break. I'll be back in under 2 minutes. So, okay. So, what were you guys discussing in the meanwhile? Any questions?
Uh,
Any
no, it
thoughts on?
was regarding his second question, which was regarding the nature of potentials. But I think we can get to that after.
Mm-hmm.
Yeah. So
Yeah.
yeah. So I was just looking at the odd potential, and so well, essentially it is the whatever, right? The the graph looks like something like a two separated like this. Yeah.
Mm-hmm.
So so at this point, so how did you force some sort of a continuity in this in odd potentials? Is I mean, is something that I had because if you have a different kind of if you don't have a exponential potential, and if you instead had something like uh, just a zero at zero, and then some sort of a sine curve, and then a pulse, two pulses going on. So I was just thinking what kind of potentials you could have that would force the continuity,
Sorry.
and
So, are you
therefore
talking
let
about
us say
potentials now or solutions? Because
uh
the exponential is not the potential. It's those are the
not
plane
the
wave solutions.
Yeah.
Yeah, I'm just questioning the nature of the potential and what kind of configurations we could have in order to, I mean, what kind of solutions you could have corresponding to the different potentials. So I was just thinking of that,
Yeah,
and
we could. Mhm.
yeah, yeah, and that's basically it, right? Like, I mean, how the pole at zero could be, try to be removed or something like that to get some sort of analytical understanding of what a potential
There
is.
might not be a pole at zero, really. Like, if you
Discontinuity, not a pole, discontinuity.
again, I mean, we're approximating this. Like they're making this short range approximation. You say that it's something distributional. So if you have a
Okay.
distribution, you have to look at things like discontinuities and so on.
Uh-huh.
If you just knew what V was, maybe you didn't have to. I mean, it's a nice way to solve it in principle by integrating it around some small part. But if you just had a step function potential, you would naturally be looking at things like discontinuities. But you could just solve Schrodinger's equation and then figure out
Uh-huh.
what you should look what it should look like. The ansatz you make for the solution is kind of dictating how your intuition goes, right? Like you make an ansatz saying that I want some plane waves, right? I just want these plane waves that are either going through or getting reflected,
Mm-hmm.
right? Then I have to start to think about, okay, there's some discontinuity or whatever. I'm solving this equation in a particular way. Otherwise, let's try to see what happens if you just wanted to solve Schrodinger's equation with an odd potential, right? So, you said sine? is that the one you were saying? Okay, let's see.
Yeah,
Let's see if we can make sense of
yeah,
that.
yeah.
So I could
Yeah, I
just
mean, like,
share a different
so
screen.
yeah, and this question goes back to the earlier question that I had, which is essentially, I mean, the earlier our prior discussion question we had, so which was essentially the why we have seen one and not C naught, why does C naught equal zero in the expansion,
Uh-huh.
right, of
Well,
the
it's not
delta
okay.
function.
So if you assume that the potential's odd, then there is no term. There's no first term in that expansion. There's only an odd. The first term is the odd term. Like you can't expand an odd function in terms of even functions. Like
Okay.
you know,
I mean that.
it's
Yeah.
property. So
Okay.
like you have a function like sine, right? So if you take sine of minus x minus sine of x. Oh, sorry. Well, you're gonna have the mad, right? Oh, it's stuck. This is very funny.
Yeah.
But you see, it just goes to minus 2 sine of x. Right? So then the point is that if I okay, so then let's could look at the Taylor series expansion of this, right? Series sine of x. Just look at 3 terms. Let's look at 4 if you want. So Taylor series is a bit more smooth than the thing that we were thinking about. But as you can see, you only have odd powers, right? So you could say that an arbitrary series starts with a constant plus x squared, whatever.
Oh.
So
Okay.
you just don't have any coefficient for x squared. Yeah.
Okay.
We could also try to solve the Schrodinger equation now with an odd potential if you wanted. Although that would be a detraction from what we were originally trying to do. But let's first get back to this issue of the Dyson series, because I think it's important. Like, you get this down once, then you don't have to worry about it ever again, because you're going to meet it. You're going to meet it time and time again. And sometimes it's worth thinking about twice, but once you have it down, it's good. So this was where we defined the S matrix. Yeah. Right. So as you can see, the S matrix is telling us how we can evolve a state at very, very early times to very, very late times. And that's where you assume. So the assumption that you can have free states is maybe justified in that limit. Is sort of your understanding of what it means for states to be asymptotic. So asymptotically, you expect there to be free states. And again, like, really you need these forces to be short-ranged for that to really make sense.
Right.
There's a lot of trouble that comes with dealing with long-range forces. So, your H naught is not just the kinetic term now. It's also the Coulombic part of the potential, because that's long-ranged. It just won't die out.
Right.
So that's led to some very interesting developments recently in the study in quantum field theory. These are called infrared issues.
I see.
So starting from here, we say that this time-ordered exponential is our Dyson series, which is fair, right? Because this time-ordered exponential is exactly the thing that we calculate. And we're going to end up with some expression like this if we sandwiched it for very long extents of time between momentum states. Now, what we could do is go through the derivation of this, or we could try to get some intuition for what's possibly going on, right?
Intuition would be better.
Yeah.
Like,
So like, how could we get an intuition for what this means here?
it's just a propagator. Like,
Why is there
what?
what is the propagator really?
So the energy of the particle minus the momentum part, and then you are giving some kind of like
No, sure.
phase.
That's the expression, but what is it? What is it doing?
So you're taking from the initial state to the final state. That's it. I mean, like,
Okay.
and saying that the particle has a particular momentum and like, yeah, particular mass or whatever.
Okay,
So
so
you're giving
what's
it
it
a
doing
rest
here?
stop. You're giving it some sort of rest mass so that it doesn't, you know.
Well, okay, so the I epsilon here really is just to make sure that this thing is well behaved when you do the integral over the momentum.
Mm-hmm.
But well, what I'm asking is, could we try to see where this could come from?
The potential.
No. Yeah. Why is it sitting between these two factors of the potential?
The contour integral, I mean, I'm just throwing,
So,
Is it
yeah.
well, okay. So the first order just comes from having one factor of the potential, and you have some initial and final momentum eigenstates, and there's a
right?
delta function here. Let's
Yeah.
try to guess
Okay.
that. Let's at least try to work out why that should be. Okay, we see why we have PF and PI, right? But that's not the expectation value of H sub I. H sub I has e power IHT per minus HT.
Right.
Mm-hmm.
What happened to them? IH naught.
They just. I mean, they turn to one, right? Or essentially
Well, they turn to one provided you're looking at what kinds of eigenstates exactly. I'm
station.
saying that there's just hinting at the fact that this delta function comes from somewhere.
Right.
Um, but,
So I'm writing E minus half P squared plus I epsilon stuff here, but here, where could it have come from, this delta function? I mean, we know that energy has to be conserved, but what's ensuring that in our series? Just a hint that wherever you see some delta function, you could think about it as a Fourier transform of one.
Right.
So it's like an integral dt,
is equal to,
right? E power minus I EF minus EIT from 0 to infinity. Or some minus
oh,
infinity to infinity.
okay. So it's like the summation of all the phases. You're taking I to EF as some sort of phase, and you're saying that the
Yeah,
integral
you
is.
integrate it over all of time. I mean, that's a guess. Now, why would EF minus EI appear there? Is another question. Well, I mean,
The potential.
it's more the nature of what these P's are, I would say. So the thing is that throughout the series, you're going to see this delta function, right? Like no matter what you do, you're seeing this delta function.
Right.
Like all the higher orders contain it. So
I mean, it's essentially from the commutator, is it? Between, I don't know.
let's try to write down certain things.
Mm-hmm.
I mean, again, people probably notice that this is very different from all of our other efforts, right? All of our other
Yeah.
episodes, but you know,
Mm-hmm.
this is what understanding these things would entail. I try to figure it out. So, okay, let's start a new block. I had some expression here. I'm just going to steal the LaTeX equivalent of it. Something like this. Where could this come from? I don't need this thing here. I don't need that thing over here. So it's the first term in the expansion of the time-ordered exponential, right? It's wedged between two states.
Oh,
Uh, one. Just yeah.
but
So
yeah, go ahead.
the right hand side, which is the sandwich between the PF, is like like equal to one. Um, but when you give it like instead of talking about the just the final momentum states, you're just giving an energy this thing. So you're kind of saying that before reaching the final state, there is some kind of a phase that happens between the energy. So there is some kind of a
Yeah. Well,
I mean
good.
like
So the thing is that I'm okay. So let's see what this could hint at. Um, we know where these P's came from. They just came from our the S matrix or where we're looking at. But we know the first term, so this somehow has to equal. Let's put an I think there's a minus I times the integral from minus infinity plus infinity of dt. Right, there's just one t here, and f
wait. Oh, okay. So is it like it is the plus infinity to plus infinity, right?
sorry, not plus,
Or is it?
minus.
Minus.
Okay, it's not, that wouldn't make any sense.
Okay.
Let's see. Okay, well, this is already progress because we know the form.
Okay. So PIHIT is nothing but
Exactly. So it's just
yeah. Okay.
P's are eigenstates of the free Hamiltonian. That means their energies are just the eigenstates of the free Hamiltonian too.
Right.
Sorry, like the energies of the P states are just coming from the
Yeah.
free Hamiltonian.
Yeah.
Right. So let's see. It's IH initial. So it's initial. Okay, no. Let me not do that. Let's just write it as is, and then we'll apply it, and then convert the operator into an expectation value, into an eigenvalue, right? And there's going to be a minus here. Sorry, the minuses are in the wrong places, I think.
Yeah. This is right.
T.
PI.
Oh, sorry. You're right.
And even in the initial expression, left hand side.
Left-hand side, very good. Sharp. Okay, we're in good shape, don't you think? Because, minus I times the integral dt e power I.
Yeah, this is what I said when it goes to 1.
Exactly, it's like the Fourier transform of 1.
Yep.
I don't know if there's a minus or a plus here. Let's see. Pi comes with a minus. Yeah, and PF comes with a plus. Okay.
P, yeah.
Yeah, you see, this is just with the eyes and stuff. the delta function of E minus EF minus EI. So there's some factors in the Fourier transform like the 2 pi, but whatever. We can see how this is more or less, let me jump a line. This is more or less going to be delta of E F minus E I.
Yeah.
Great.
The 2 pi is also picked up during the Fourier transform.
Yeah, exactly. So I just haven't committed to conventions of the Fourier transform and the inverse Fourier transform, so I'm kind of shy from writing it down, but that's essentially where the 2 pi comes from, the I and the 2 pi and so on.
Okay.
Right, so this is like using the delta function. The fact that the delta function is really a Fourier transform of 1. Right. You see, this is like a time inverse Fourier transform of 1.
Right.
So here I've just sandwiched the first order term between two momentum eigenstates.
Right.
What happens if I have a product now? Right? It's like
product.
Okay, so let's go to the next order, right? So again, real quick switch so that we know what we're talking about. Mm-hmm. So we got this down.
Right.
And this means that we understand what happens to this EF minus exactly. Okay. So let's be a little bit more careful. We know what happens to EF and EI at the extremes of V. Right?
Yeah.
They always come together this way.
Right.
But that's not the only thing we need to deal with. Right?
You just insert, yeah. You just
Exactly.
insert
Resolution of 1.
complete basis of P
Exactly.
in the middle. Yeah. Okay.
So now things are going to get a little bit more interesting, gentlemen. And let's see how interesting they can get. And we'll learn something very nice about the propagator. We'll learn something about how the propagator relates to what's called a Whirlline formalism. But this is, okay, good that we're doing this. Okay, well, this is an accomplishment that should have its own section. Fine, I will go here and then say S matrix expansion. So once we get this down, I'll just give you a sense for the reward for this effort. Because anyone who's listening that's not us right now might be wondering, or even you guys might be wondering, it's all great. You put a lot of effort into showing us how to expand something in quantum mechanics in one dimension. Who cares? Right. Well, right. The reward that you get from going through the pains of this exercise is that So to whoever is confused about the point of this and feels like they're putting an awful lot of effort into understanding something in just quantum mechanics in one dimension, they needn't worry, because whatever happens when you look at the S matrix in any other setting, right, in quantum field theory, boils down to exactly this. This is all you're doing. All you're trying to do is compute these matrix elements of V, the interacting part of the Hamiltonian, whatever that might look like. Right. And then what will happen in field theory is, okay, you have a number of different dimensions. You don't just have one momentum, you have a few different momenta, right? You have like, okay, 4D spaces worth. I'll give you some different factors, okay, but fine. Right. The next thing we're going to see will be exactly the same, as to see where the propagators come from. But evaluating the matrix elements of the interaction parts is exactly what the vertices of the Feynman diagram are.
Right, that's true.
Oh, okay.
When you see how they're sewed together with propagators, you realize that's exactly what this what the expansion of the S matrix in the Feynman diagrams means. So
okay.
fear not. This isn't this isn't a total waste of time. But okay, so now we're after the second order term, right? So let me again steal the expression so that we can go to our work board. Okay. So far, are you guys following or enjoying this?
Yep. Yep.
Okay, great. Yeah. So start here. Great. Now let's go back to our sheet. It's not acknowledging. Okay, it is. Great. Okay, so let me just copy down that expression again.
Mm-hmm.
Let's kill the right. Let's kill the plus. So Pradyot had anticipated something, right? But let's first look at what the second order expansion is. So okay, once we do this, sorry.
Just clarifying. So that is a DP, right?
Yeah, DP.
Okay.
Very good. So this should come from minus I squared, I think. And this is where we have to remember that our integrals are all ordered, right? So now we're going to the second order, and we're going to have to play a little bit with the time integrals, like the order of the time integrals. So the first integral is from minus infinity to infinity.
Mm-hmm.
Times dt1, right? Of always we're taking the sandwich between pf and pi.
Mm-hmm.
Yeah.
Yeah.
But now we're going to have two factors. H I H I, because this is going to be the second order term in the series, then what's going to happen is that this is going to be t. Oh, wait, I've missed out on an integral. So right here we had dt1, and we're also going to have a second integral,
Yeah.
dt2.
Yeah.
Okay.
2, but now let's be careful about this one's bounds, because that's going to be
And then, yeah, this is
1.
minus infinity. Oh, wait. Okay.
Yeah.
This is because we're expanding a time-ordered exponential. This is the meaning of the time ordering.
Right. Right.
So we'll have to come around and maybe understand that part too at some point. But you see, it's going to matter because I'm going to have here T2, and here I'm going to have T1.
Yeah.
And clearly we see an integral dp on the left-hand side that we don't see on the right-hand side.
Okay.
So let's insert that. Let me copy down the integrals I had before, the time integrals. Okay, this is going to be great. Everything's going to make sense. And now what could this dp possibly be doing for us? We're inserting a resolution of identity, right? So we want pp somewhere.
Right.
Right? We see this p and p. So Pradyot rightly pointed out that that must have been what has happened here. Right? So now let me take, for effect, let's take this. And then between these two, I do
Yeah.
okay. So now we have ourselves slightly more interesting set of energy integrals.
Mm.
But let's resolve all that. Okay, so let's first get this expression in terms of v. Right, so we have everything before except where we have h sub I of t1. What am I going to do? I have e power I at h naught t1. Bad. H naught t1. Frustrating. Hat v e power minus I hat h naught t1.
Yeah.
We're happy with that?
Yep.
Now let's just copy this and replace some expressions with other expressions. Right, this is going to be t2, this is going to be t2. Very cool. Now, let's see if we can count our E factors. There's going to be EF T1. And we have to just call this E. Let's just, because we don't have any other, okay, there's no subscript on P, we call it E, okay? So we have E minus I E T1. We have plus I E T2. And we have minus I E I T2. Okay, that's a lot to think about, but let's write it all down. Okay, so now I copy this. So this is our collection of integrals, right? Let's remember there's one, this is going from minus infinity to infinity. Second one going from minus infinity to t1. Okay, and there's a dp, but you know, all these e factors don't care about it. So let's do this. Actually, let's not. So let's just get the e's to come out near their definition. So we're going to have to be careful about this. Let's just replace them where they stand with the eigenvalues instead of the eigenfunctions. So sorry, instead of the operators. So here we have I, E, F, T1, right? Put it here. Yeah, I'll put it here. So we collected that one. And then we have hat V. And here we're going to have something different. We're going to have E power okay, let's see if I can get this right. So how do we make sense of this at some generic time? It is just minus IET is one thing you could say.
Maybe it's just an intermediary term, so
Let's just keep that for the time being. Let's see what we can convincingly pull out and what we can't.
okay.
Because we need the propagator to come out at some point. That's what I'm keeping an eye on.
Right.
So I'll just give you a hint. The propagator comes from a very similar integral as what gave you the delta function. That's the hint. So what could that be though? So minus I h naught of t, that's just p squared. P squared times t, right?
Right.
Okay.
Okay. So let's that's why I said let's keep this inside the momentum integral because we're going to need it.
Mm-hmm. Then you have P.
But okay, so I just put t here irresponsibly. It's t1.
Yeah.
Right?
Yeah.
T. Okay, and here we have e power I. Again, we're going to discover if this should be an overall sign or not. I apologize for the frustration. I think it's p squared over 2. That's our free Hamiltonian.
Yeah, p squared over 2.
I'm not wrong.
About that. Yeah.
Yeah. So two. And what's the time going to be? T2.
2.
Right?
Yep. Then
Had
pull
to
out
be.
another E term.
Yep. This is going to be minus IEF.
EI, right?
No, EI, sorry. EI, T2.
Yeah.
T2. Okay, now we can collect everything that's non-operatorial and then separate the matrix elements.
Yeah.
So there's stuff that's operators, stuff that's not operators. Let's demarcate then. Once again, we have our string of integrals. Very good. And now we have string of exponentials.
Yeah.
E to the power. Let's just add them. I E F T. What now, guys? 1.
Yeah.
1.
E to the power
minus I P squared over 2. Are we in agreement?
Yep.
T1. So this is T1. And then I have another exponential.
Yeah.
I.
P squared.
So I have minus I E
I
T2. Correct. Minus. Plus. Minus.
Minus. Yeah.
I
mean brackets of
plus.
minus, right?
Yeah. If it was bracket, I would put minus, but now plus I. left, right, squared over 2 times t2. I don't know why that one got a big bracket and the other one didn't, but I hope that this is understandable.
Yeah.
And then we have something we recognize.
Just a vertical there. And
Yeah, I missed it. Okay. I don't know. Wait. Get rid of this. Add me is fine. See, PF here. Okay. I don't know why there's 2 of these. I don't need that there. P, and we're almost done with this line.
Yeah. That is Cool.
Yeah, well, now we're seeing something. So the T1 integral can be pulled straight in and done.
Yep.
The T2 integral is going to require a little bit of cunning.
Isn't it the other way around, or is it?
We could start with the T2 integral.
Yeah.
So the T2 integral, what's it going to be? It's going to be this. And now we need some help, right?
Yeah.
Let's consult Dr. Mathematica for some intuition. Okay, because what do we have? So it's not the Fourier transform of 1. It's like the integral from minus infinity to some random time of an exponential, right? Okay, so let's see if Mathematica can tell us what that is. Or maybe we have to be more clever, but okay, so now I want you integrate for me the exponential minus, so it's like I a times t from where t goes from minus infinity to k. I really hope that this will happen in reasonable time. Could be that Mathematica is the wrong place to look for it, though, because it struggles with certain things.
Right.
You know, ideally, I would have put the effort to specify that k is like real positive, something like that. But now it's going to try to do this in the most general case and tell me what the expression is if k has the imaginary part. You see the imaginary part of a is less than 0. Which means that if I did this, right? Okay, so good thing I should stop complaining about Mathematica because it just delivered. But it also means that if I did this,
Anytime though.
anytime.
Yep.
Oh, wonderful. So that means that if I have e power minus I times something time, that I integrate from minus infinity to some constant. It could be 0, it could be k. It doesn't care that there's a k there, right? But k is not infinity. Then I get the inverse, I over a, the inverse of the thing in the exponential.
Right.
Okay, maybe take a second to digest this. Pradyot looks apprehensive.
No, I'm just trying to do the calculations in my head. I don't trust mathematics.
Okay, so tell me how you do this calculation in your head, and then I'll.
I'm fine. Yeah, I'm fine. I'm
I
comfortable
mean, this
with
this
it.
is actually fine. You could probably do the. Sorry, I A K, so you'll get K there. But this is something we can do. I was just being lazy. The exponential is one-dimensional exponential is pretty easy.
Yeah.
Yeah. So
Yes.
it wasn't even entirely necessary to consult Dr. Mathematica. But let me go back to our notes. Okay. So let's come back to our exercise.
Yeah.
I hope you guys are finding this as exciting as I am.
Yeah.
Because it truly is a pain when you don't get enough time to do something like this.
Mhm.
So now let's eye the T2 integral, right? This is a minus. Let's rephrase it in terms of the knowledge we just gained. So okay, I'm just trying to find it. I want to take minus I outside, which means that I have to change this sign. What do I have to do actually? I have to just change this to minus. All right?
Yeah.
Yeah, and then there was a stray
Bracket.
which I don't have the patience to track down, but maybe I should.
Just after T2. Yeah.
Just 1 second.
Yeah.
This is starting to look good.
Yeah.
What is this telling us? So let's do the T2 integral.
Right.
Right. Next line. I'll just copy everything down because this is a right mess.
Out. So, oh yeah, finally we get something that resembles the answer in the denominator.
Yeah, you were getting there. We're getting there. So what did we have here? Let's keep our like T1 stuff preserved. Let's just keep it all as it was.
Yeah.
Right. This is the mess that it was. I also brought the T2 stuff, but let me reshuffle things. So I take integral T2. So I cut it. Right in front of this, I go here. Oh, sorry, wrong place.
After E2, yeah, there. Yeah.
And I have the rest, which I'll just write down like this.
Yes.
Actually, no, let me not be lazy because that's gonna confuse the viewers at home. However many in number.
Yeah.
Not. Okay, so Dr. Mathematica taught us that the result of this integral will be all this amazing stuff. Okay, well, it's running over the line. Let's not do that. All this amazing stuff with our final integral, right, that comes right before this, being replaced by what? Being replaced by a ratio of an exponential function.
Yeah.
And rational function.
Yeah.
Right. So so let me just erase all of this, and let's just, so it's ei minus p squared over 2. Let's just remember that. Right. Kill all this. E to the power I left and right. Wonderful. So it's ei minus p squared over 2
P2
divided by
isn't there a T2 there?
Oh yeah, there is a T2. You're absolutely right. But I was more anxious about getting this bracket down. Sorry, there's a T1 because we did the T2 integral and the integrals from minus infinity to T1.
Yeah.
But very good, very good. EI minus
T square over 2. Yep.
and okay, well, we might as well add the I epsilon here. This is just to say that when we think about doing the P integral, we need to deform the contour. There's really a contour integral here. You're going to take epsilon to 0, but let's just add the I epsilon right now. We're not really thinking about doing the P integral, so in some sense, we don't need to put it there.
Right.
But eventually, you're going to have to do it.
Right.
Now we have just the T1 integral, and it'll give us a delta function. Don't you think?
Yeah.
Let's see what that delta function will be. Wonderful, wonderful.
Yeah, it's good to see something that resembles come through by now.
Oh, well, we're almost there. What do you mean just resembles? Let's take dp outside, right? Yeah, so we have our integral over T1 now. But since it's the last integral left, we don't really need to think about it as T1. We could just call it T, right? It's just an integration variable. I just replace it everywhere. Or if it's just confusing, let's keep T1. And I'm not that lazy. Well, infinity, not the infimum. Very good. And now we have an x. Let's just separate out the exponential parts. And we know where to put the rational function. We can put it between the V matrix elements, right? Suggestively. So what do we have here? We have not IE, E power I times EF.
EFT1.
EF minus, well, let's see. Is it a minus? Yeah.
Yeah.
Minus P squared
2 plus EI
over.
plus EI.
Sorry, is it a minus or a plus?
Shouldn't it be? Hey.
I think that there's been a plus or a minus that we played with the wrong way somewhere. Because what's going to happen here, what should happen here is that the P squared should cancel.
We forgot minus.
We forgot the minus. Very good, very good. In our previous expression. Are we in agreement?
Yep.
Wonderful. So now we can get rid of this unsightly thing. Two minus E sub I times
Yes, finally.
Well, let's just get the, this is just so frustrating. Okay. Let's just wait for the computer to respond. Although quantum field theory is relativistic, this computer is not. Okay, P. No, V. Okay, and now let's do I.
Over.
So the mind-blowing thing that I was trying to tell you guys has already occurred. You see, the propagator is really the inverse of the free Hamiltonian.
Right.
Remember our formula? It
Yeah.
was a 1 over A. A is the Hamiltonian.
Yeah.
Right? So if you took the free particle Hamiltonian and then just took its inverse using this formula, that's the propagator.
Propagate. Right.
Right? And that'll be the same in quantum field theory, except you're going to be dealing with the relativistic particle, the free relativistic particle.
Right.
2 plus I epsilon.
Yeah, I'll have to still look
Oh
at.
wow, Shire Neal is early. let's not make fun of him though. I'm glad he even showed up. Honestly.
Yeah, I still need to look into the epsilon aspect of it.
Yeah, we could do that. We'd be happy to. In fact, we could just think about it purely in terms of the whirl line.
Right.
You know, in terms of the whirl line of particles propagating and so on.
Right. Right.
Great. So now let's see. What can we do? We can cancel these p squared over 2's.
Yep. And then
Okay.
I think there's a T1 message.
Oh, very good. Very good. Been catching T's all day. I've been missing them all day. Gone. And we know how to do this integral.
Yep.
Sorry, so this is E, what was it? I, right?
Yeah. Yeah.
But you see, what will happen now is that this integral will give you a delta function that sets EF to EI, which means it doesn't matter if you're using EF or EI, you could just call it E.
Right. Right. Yeah.
Okay, so there was a 2 pi, there were some other things, there's an I. I'm not going to keep track of any of that. I finally get something that goes like integral dp with a delta function 2 pi delta EF.
Yep.
It'll come. Minus EI.
Yep.
I of the rest, which is what we started with.
Yes.
So congratulations to us.
Yay. Hola.
Right? So now you can imagine how the rest of this will go. You're always going to have these intermediary time integrals that will always go from minus infinity to t sub x, let's call it, right? You have some n terms and x is one of the terms. And how the time ordered product works is that you always have these integrals from the lower bound to some time. And that time is going to be the next integral.
Right.
Which means you're going to have nested products of PVP, this matrix element, propagator, PVP. And all those propagators are coming from what?
The Hamiltonian free particle.
Exactly, the inverse of the free Hamiltonian.
Inverse. Yeah.
Right, so it's really like you're taking the propagation along the whirl line from minus infinity to some time, and that's why. So you see, like why, like that expression that we got from Mathematica is just telling us why that's true that we think about the propagator that way.
Right. Right.
Right. Let's go back to that, because I think that is probably the most enlightening thing about this whole exercise that we've done, which otherwise is just a lot of work.
Mm-hmm.
So great, we got this back, right? Now let's go. Yeah. I don't know how I'm doing this. Yeah, back to this. What I want to say. Oh, it's not happening. Okay, my computer is getting super slow now. Why is the propagator propagating? right? So let's go back to our famous formula now.
That's what a propagator does.
Yeah, sure. But
Question here: when in the denominator you have EI minus P squared over 2 plus the I epsilon stuff. So in
yeah,
that case, is P the 3 momentum or the 4 momentum squared?
one momentum right now. We're in one dimension
Okay.
of quantum
All
mechanics.
right. Never mind. I'm very much
This is
off.
just sure. This is just our how should I put it? Our exercise from the
Right. Okay.
Yeah.
this
So
is
P
just we're
squared
just
is
deriving.
not. So P squared
It's
is in no way
literally
related to the mass M squared
no.
pole that we generally
It's
see. Okay.
here you have a pole at E squared equals P squared over 2.
Yeah.
Okay.
This is the analog of the on-shell condition. So the point of this
Okay.
exercise is that you have a direct, I mean, as what you're alluding to is that there's a direct translation between all of those notions that you have in quantum field theory directly into this example,
Okay.
right? Like
Okay.
no example of the Dyson series is any different, right? Like energy, I mean, this E minus P squared is exactly like, omega squared minus P sub I squared plus whatever, right? And this delta function of EF minus EI is the thing that, well, you can kind of see how this is going, right? You have a D4P that you're turning into a D3P, and then you're, collecting these factors of 1 over 2 omega and stuff. So we can go into that on another occasion. But
So
yeah,
just another thing then. So when you say that the pole is at E minus P squared, is that the on-shell condition for a massless particle?
could you say that again? When the pole is at E minus P squared? No, it's the on-shell condition for a one-dimensional non-relativistic free quantum mechanical particle. So you're right, it looks like that, but here it's just 1D quantum mechanics. So this is our famous formula, right? So it's like minus IAT
Over
equals I times, sorry, this is, let's just go back. Let's call this T, let's call this T1, right? Is equals I e power IA T1.
over A.
Exactly.
It's minus A, right? Like minus.
You're right.
Okay.
So now let's look at some expressions that might ring a bell. Remember this?
Mm-hmm.
You see this? You see this 1 over A? You can kind of see where it's all coming from, right? So when you're in the interaction picture, that's literally what the propagator is doing for you. It takes some state that looks like this side trial, and then, the effect of integrating from minus infinity to T, which is the effect of integrating with the free propagator, is, taking you to any other time. So the point of all this was to clarify one of the steps in this exercise, you could say. But one thing we got was that this is what the Dyson series will always look like. You're always going to be evaluating matrix elements in momentum space of the interaction Hamiltonian. You're going to be integrating over propagators. You're going to be looking at states that always conserve energy, right? There's going to be a delta function with energy on the outside all the time. And in fact, we can actually replace E sub I with E. It doesn't actually matter because energy is conserved by the process. Right. So that's one aspect of it. Another aspect of it is that the reason why we will have trouble, right? The trouble comes from this integral in the example that I showed in the video. The trouble comes because you're inserting a complete set of states, right? You're summing over all intermediary states.
Right.
And in quantum mechanics, there's intermediary states of arbitrarily high momentum, and consequently, there's going to be position eigenstates of arbitrarily short length.
Yeah.
Right. So these are the sort of reasons why you're going to have to deal with this. Now, we could have played this game in position space, and that would have been kind of interesting. It would have been much harder to make sense of various things here, but just because H is naturally given in terms of P, but it would have been a nice game to play nonetheless. But yeah, now we can kind of
See, yeah,
go back to the exercise that we were dealing with before in this video, where basically we said that we want to parameterize the sensitivity of an observable at some large distances to what happens at short distances, right? And that's the role of the renormalized coupling. Why there would be sensitivity in the first place is because of the fact that these intermediary states involve arbitrarily high momenta.
yeah,
Right. So really, when you're regulating, what are you regulating? You're regulating this identity that a sum over x or p of xx or pp is 1.
yeah,
Right. So that's sort of the catch here. And again, the fact that you were playing this game with the distributional potential in the first place was all because you started by looking at a particular subsector, this long wavelength subsector of these scattering modes.
yeah,
Right? If you just solve the Schrodinger equation, you'd be fine.
right,
With some odd potential, you're probably going to be fine.
right, right,
But then again, maybe you won't. So take a random arbitrary, short distance potential, or odd short range potential. Say it just there are no solutions to the Schrodinger equation with that potential. But say you only probe it with some long wavelength modes. That equation is fine. You just have to know what C sub r is. Yeah, you just have to infer C sub r
yeah,
from A, B, and C, and you're fine. You can play with this, right? Despite the fact that secretly it just doesn't exist. This is a manifestation of the worry that people have about some, like the standard model plus general relativity. So, some seemingly non-renormalizable theory. You're like, oh, okay. I mean, I actually never really know. Like, I just have to keep going and measuring all these other things, like all these other coefficients of that multiple expansion. And maybe if I keep doing that, I'll be fine. But maybe at the end of the day, it just doesn't exist. Okay, clearly that can't really be true because we see that general relativity works, but it's not as forgiving. And so, if you're just trying to simulate theories and you want to run a simulation for the universe, you'd be concerned that I want something analogous to a Schrodinger equation that I can actually solve.
yeah,
That I'm expanding and then I'm getting all these things, coming out of.
yeah,
Right. And clearly that's not just going to be in the form of these long wavelength modes, which means that what you started off with dealing with as an effective field theory might not be an effective field theory at the end of the day. Like fundamentally might just be something very different. But we'll get into all of that and more once you think about the renormalization group and so on.
yeah, group flows and stuff.
Yeah.
All right. So there's nothing else. I'll just end the recording.
Yeah. We've done a lot.